previous speakers for their very nice talk so far. I may apologize that I used the blackboard, and I do hope that this is not going to be an eye exam for the last people sitting in the row. I try to write as large as possible. Nevertheless, I do hope that I have some time to cover some material. When I prepared my talk, I realized that that might be a little bit too much stuff I want to explain. So maybe it's about minimizers in this theory, and the blow-up part won't be too much detailed here. So, okay, let me mention that this is joint work with Mathieu Levine, and also parts which I might not be able to explain is also joint work with Benjamin Schlein and Christian Heinzel and Mathieu Levine. So, I try to motivate the kind of problems we're interested in by giving, first of all, some kind of historical motivation. Actually, it's about the stability of stars, cold stars. So you might think of neutron stars or white dwarfs. So temperature does not play any role anymore. Only gravity, so to say, decides, and the mass of the star, what will happen. That this might, up to eternity, be a final nice state, or it might eventually collapse by gravity to something else, which you may describe by using general relativity, which is not the issue of my talk, but some kind of onset of gravitational collapse, which is quite well described actually by a mixture of special relativity and Newtonian gravity and quantum mechanical input. So the basic starting point is due to Chandrasekhar in the 30s. So actually when he became a graduate student here in Cambridge, England, when he came from India, he was on a boat travel, and then he had apparently enough time to do some calculations, and he, so to say, combined, which was then recently discovered, quantum mechanics, in particular Fermi statistics, so many-body quantum mechanics, with Newtonian gravity, and tried to figure out states of matter which can be attributed to stellar systems. So he gave a very short argument, and in fact this argument then was later, just a year later more or less by Landau, put in some kind of energetic argument, and this is the argument you should today, it's a heuristic argument of course, should to give him insight. What the claim of Chandrasekhar is that he claims that a star with a mass which exceeds the solar mass by say a factor of 1.4 cannot exist. It will maybe eventually collapse to something which back then was of course not known what a black hole is, but this was, so to say, a source of lots of kind of arguments in the astrophysics community. And eventually Chandrasekhar was, he was a grad student, and here in Cambridge no one believed him. There was a big prominent astrophysicist called Eddington which said this is complete nonsense. And only 50 years afterwards, in the 80s, Chandrasekhar got its Nobel Prize for this kind of insight, basically. So what is the basic, argument, back of an envelope, that you can think that the total energy of a star, which is just given, say, by a semi-classical description of the kinetic energy of relativistic fermions, which would scale like 1 over length, and a non-relativistic system would be like 1 over length squared. But this is essential that gravity, which then is also a potential energy in your system, also scales like 1 over length. And then you only have some kind of coupling constant here appearing, and the total mass of the star maybe in terms of m squared. And then the argument is just to see that this is, well, it's very simple to see. This is bounded below if this m is sufficiently small, and if m is sufficiently large, this energy is not bounded from below. This is basically the argument that, so to say, generated this theory of gravitational collapse. And just as it's unbounded if m is, say, sufficiently large, and you have exactly a critical threshold you can calculate if you put in certain numbers, and everything is fine. And by the way, it's a very interesting physical constant, because all the fundamental constants in nature appear. So h bar enters, so quantum mechanics somehow plays a role, which, so to say, comes in this expression for the relativistic kinetic energy of fermions. Newton's constant of gravity enters somewhere here. And also c, which is not the c here, the speed of light also enters the kinetic expression. So all the fundamental constants of nature do play a role in order to, so to say, find the numerical value of this critical mass, which is called the Chandrasekhar mass. Okay, so but this is, I mean, this is really rough physics, and my interest is, say, threefold here, and also of some other people. So to say, to have some kind of program about these claims. Yeah. So first thing, which was then the initial impetus to study this Chandrasekhar theory on mathematical grounds, was, so to say, a derivation of a rigorous derivation from quantum mechanics to understand this kind of quite heuristic calculation on a rigorous level coming from some kind of microscopic model. Then, of course, this kind of argument is not any, if you want to talk about gravitational collapse, this should ultimately be a time-dependent process, that something really collapses as time goes by. And this is just a purely variational argument. This is, so to say, a variation of collapse. So ultimately, you might be also interested in some kind of dynamics. Study maybe effective nonlinear dynamics, which are, in a sense, rigorously derived from a quantum mechanical description, and then you might want to understand the finite time blow up, a singularity formation of these equations, or even just prove that such things do exist. And then the third part would be that mathematically, or also physically, this is a fermionic system of many particles with attractive interactions. So the gravity, of course, an attractive interaction. And as we have seen in some talks before, that Cooper pairing or pair formation might be something which is both of physical and also mathematical interest. So you might want to understand mathematical models which incorporate the effect that these fermions can, due to energetic favorability, form Cooper pairs. I should say, of course, a warning right in the beginning, these Cooper pairs in these descriptions would be due to the gravitational attractive interaction. And in a real physical model of a star, the Cooper pair formation would be maybe due to some nuclear forces which are way much short-range forces. So hence, if there is pairing by gravity, the pairing scale is maybe quite off. I mean, the pairs have maybe a distance which is much too big. Nevertheless, this is still an interesting topic you should be interested in, and of course you might be in the end also try to incorporate other forces which also might indicate the existence of Cooper pairing. Okay, so let me try to give some kind of then motivation from the mathematical physics literature. So it started out, actually, the rigorous study of this kind of problem started out with some work in the 80s by Lieb and Thiering, and then later by Lieb and Yao, which considered the following setup. So in the 80s, Lieb and Thiering, and I also said Yao, there's no, it's just separate papers by Lieb and Thiering and then by Lieb and Yao, but let me just write it like this. So this was basically in the 80s, 84 and 87. They, so to say, initiated a rigorous understanding maybe of the Chandrasekhar theory of gravitational collapse. That is, that you take some model which incorporates special relativity, but still maybe on a quantum mechanical level. So Chandrasekhar actually used some kind of semi-classical approximation already. So you want to have a kind of microscopic relativistic model, but you still keep Newtonian gravity. So the many-bodied Hamiltonian proposed by Lieb and Thiering and then later studied by Lieb and Yao is just of this form that you take a sort of relativistic energy, kinetic energy, this form, so n particles, capital N particles, this is the relativistic kinetic energy. Fermionic nature will be just imposed that this Hamiltonian acts on antisymmetric wave functions. And then there is a potential energy part, which is just of this Newtonian. So acting on L2 antisymmetric. I completely neglect spin in this. I mean, you could of course include spin and so forth, but this is nothing essential here. So let's ignore the spin and talk about spinless fermions, just antisymmetric functions in the space R3 times n. All right. So the first result, then Lieb and Tiering, so to say, looked then at the, so to say, recoupling limit, and this is a very useful and reasonable regime when you send the number of particles to infinity, which astrophysically is, of course, a very, so to say, limit which makes a lot of sense because there are lots of particles. On the other hand, this coupling constant kappa is typically a very small number, so mathematically you might also then send at the same time kappa to 0, but in such a way that you have that the product of kappa times n to the 2/3 is a fixed constant. So this 2/3 actually has to do that you have fermions, which, so to say, if you fill the Fermi levels, the kinetic energy scales according to a certain power of n. And if you choose the coupling constant in such a way that this is true, then the potential energy is of the same order as the kinetic energy. Hence, in a limit, you might expect that you get something which has some kind of reasonable result. And in particular, you might want to understand the ground state energy of this problem. So the infinite spectrum of H kappa n. And what Lieb and Yao then rigorously did is they derived in this limit the Chandrasekhar theory by looking at this quantum mechanical problem. So then the result was you obtained rigorously Chandrasekhar's theory in this limit. In the sense that you see that the ground state energy is then in this asymptotic limit given by the ground state energy of this Chandrasekhar semi-classical functional. It was maybe today not a big surprise, but in the 80s this was a result which also initiated the study of the stability of matter. And also you can say something about the minimizing solutions. Actually, this is a translational invariant Hamiltonian. It does not have an L2 eigenfunction at the bottom, but you can still make sense of an approximate ground state. And this is also something that Lieb and Yao considered. So this was back in the 80s work, which, so to say, triggered some interest in this kind of problems. And then more recently, you can also think about the rigorous derivation in terms of the dynamical problem. Elgart and Schlein in 2007 considered the dynamics. However, they considered the dynamics of the same Hamiltonian in a bosonic theory. So they consider symmetric wave functions, and you might think of this being a boson star, which is less physical, but nevertheless an interesting mathematical theory. And then you can also consider such weak coupling limits, n going to infinity, also kappa going to 0, but you have a little bit of a different scaling rate between kappa and n, and now it's kappa times n, which has to be kept fixed. And what they then rigorously can do, they can see that in this limit, you obtain basically a single Hartree type equation, which is also physically quite clear, but rigorously this is quite an interesting amount of work already. The full fermionic dynamical system is maybe hard to treat because here in this setting you can study product states which have a very nice behavior, but in the setting of fermionic systems, the rigorous derivation of dynamical evolution is still quite an open problem. So what you can do is you can, of course, come up with some kind of ad hoc nonlinear models which supposedly describe effectively the dynamics of this many particle system, but this is still not fully understood. Okay, so this is basically some kind of motivation. So I will, if I was in a more PDE conference type, then I would then immediately go to this very nice clean scalar PDE, but let's be more physical and try to study the fermionic system, which also has interesting properties because of the Fermi principle. You get also different qualitative behavior, which is also here reflected to the fact that you have this different power here, which physically means that stars in this theory have much bigger mass. These stars are very tiny. This is a constant of order 1 that you can see that you get a stable star. So the number of particles that you can put into a stable relativistic boson star is quite tiny. But here, because of this power, you really get some kind of really extended star. And let me also mention, this is in very good agreement with all astrophysical data, that this is really, if you plug in all these numbers in these calculations, you get this effect, this 1.4 times solar masses. No kind of stable star has been ever observed, zero temperature star, say neutral star or white dwarf, which exceeds this mass, except for some specific examples, which are some kind of discussion today. Okay, so what I want to do is now I want to present a Hartree-Fock-Bogoliubov model, which, so to say, arises from this many-body theory when you restrict it to a set of quasi-free states, and then you can effectively discuss a nonlinear model which shows quite interesting features. In particular, it also has the possibility to study the question of Cooper pair formation. So what I want to do here is that I want to do the following. So I will now come to a variational problem which also generates a dynamical evolution, but I will be mainly concerned with the variational problem, that is with the time independent theory, and first discuss these issues. So what's the model? So the model is the following. So you restrict now this many-body Hamiltonian, fermionic many-body Hamiltonian, so acting on this antisymmetric space. I again completely neglect any spin issues, to a set of quasi-free states. Hence, we have now effectively a set of operators which describe this kind of theory, and I call it capital gamma. And there's a little gamma inside, so I should write a little bit bigger here. And there's an alpha, there's an alpha star, and 1 minus gamma here. No, there's a minus here. And so little gamma is a trace class operator, one-body density matrix with certain properties, of course. So it's a self-adjoint operator, and it satisfies this inequality. And then there's another operator, this alpha, which so to say covers the possibility of pairing, and alpha is just a Hilbert-Schmidt operator. Nevertheless, they are connected by some kind of operator inequalities. You cannot just choose them independently. This is also an important fact when you discuss the variational calculus attached to such problems. Yeah. There's a minus here.
Maybe norm.
Yeah, sorry, thanks. And again, there's another condition. So this, of course, implies that this is a self-adjoint operator, complex Hilbert space. But this Hilbert-Schmidt operator also satisfies the symmetry condition that if you take the transpose, so think of this being kernel of this operator, that you get a negative. So again, if you had spin variables, it would be maybe more natural to put this antisymmetry into the spin part. I ignore this issue for a second. So my set of variables, which I want to minimize over, is a set of these are operators, in fact, and they have to satisfy certain conditions. I mean, trace class, Hilbert-Schmidt, and then these conditions. And then there's also an inequality which has to be satisfied. But once this is fixed, you can write down an energy functional and try to do some variational calculus. Okay, so next condition is then, which you can write in a very simple fashion, that this whole 2 by 2 matrix satisfies this operator inequality. And in particular, this gives you, for instance, a non-trivial relation between alpha and gamma. In particular, when gamma is a projector, so gamma squared is equal to gamma, alpha has to be 0. So you see there is a certain kind of relations among these operators. Okay, and again, I should mention when this pairing matrix alpha vanishes, we have what's called just a Hartree-Fock state. But Hartree-Fock-Bogoliubov incorporates the possibility of pairing. So what's the energy functional now related to such a setup? So coming, of course, from this many-body theory, is that the kinetic part is now the trace of this expression here with little gamma. This is the kinetic energy of the system. And as you may well know from other Hartree-Fock type approximations, you get now a direct and an exchange term which will involve the gamma, and which in our case looks like this. So there's a part which is of this form. Everything is in R3, so these integrals and so forth. So there's a direct term when you take the diagonal of this one-body matrix, and then there's an exchange term coming in. And our potential is just the attractive Coulomb potential. So this is the main interaction because of gravitational interaction. And then there's also another term contributing to the total energy coming from the pairing. So you get a second term, which is of this form, looks quite similar to the exchange term, but it has in fact quite a different nature when you study it variationally, which is of this form. Then there's a third term, which is the pairing term. Okay. So when you try to minimize, and suppose now this is, so to say, your problem that you want to do is you want to optimize or minimize this energy over all these these states, which are described in terms of this capital gamma, say, satisfying the side conditions. And of course, we have to fix another condition which corresponds to the total mass or number of particles in the star by fixing the trace of this little gamma. And then we have a well-defined variational problem, and we might want to understand the minimizers of this kind of variational problem. And this led us to a very interesting variational problem, as we believe, because it's quite different from other variational problems, say like atomic Hartree-Fock, where you have a repulsive interaction, there might be an external potential, and so forth. You have to deal with many kinds of difficulties which this functional brings in. But let me first state the variational problem. So what you finally want to do is you want to study the infimum of this energy, gamma satisfying, of course, these conditions, and of course there's a kind of a natural energy space attached to this. So gamma is not just trace class, but this trace also has to be finite. This is, I skip this is very straightforward. But the side condition that we fix is that the trace of this little gamma is equal to lambda. Lambda is your variational parameter. And the first, say, very basic observation, just using inequalities, is that you can first study whether this functional is bounded from below or it's not bounded from below. Huh? So in a sense, this reflects the Chandrasekhar argument that there's maybe a certain critical threshold lambda where this problem feels to be bounded from below, but if lambda is maybe sufficiently small, the function is bounded from below, and then you want to understand maybe that there are maybe minimizers and so forth. So the basic observation is that there's a certain universal constant, depending on this kappa and here maybe, that this is larger than minus infinity. Depends on kappa. And I should also say that kappa absolutely has to be small enough. 4 over pi. Turns out if you choose your lambda as small as you like, but you switch on the kappa, you can always beat this term in terms of this using kind of a Hardy inequality. So there's also an absolute requirement on the smallness of kappa, which physically, of course, is not very harmful because kappa is typically a very small number, much less than 4/pi. But then it's minus infinity else. So if kappa is larger than this, but the more interesting case, if lambda is larger than this universal lambda star. So what are the problems with this kind of thing that you now want to try to understand the variational calculus attached to this problem? So now you want to maybe understand whether there are minimizers, in fact, in this regime. Okay. So the first thing, which is, so to say, in striking contrast to Hartree-Fock theory in atomic physics, is that the function is not weakly lower semi-continuous. Easy to see that this is not weakly lower semi-continuous. So you cannot just use a very direct argument to prove existence of minimizers. This is because of the gravitational interaction that you can, so to say, easily see that this function is not weakly lower semi-continuous with respect to some weak topology that is naturally associated to this problem.
So with respect to which topology?
So you have a energy space here, which is it's a certain 1 class for the gamma, and then there's a Hilbert-Schmidt norm for the alpha, and the weak star topology associated to this. So you should call it weak star lower semi-continuous. But I think it's quite usual in this kind of thing that you drop the star. But in the paper, it's of course done right. Translation and invariance, well, this is another problem. It might be you have to deal with. This whole function is translation invariant, so also your minimizing sequences could, in a sense, escape to infinity. This is not a very big complication. You can deal with this, but nevertheless, this is also something you have to take into account. And then there is a fact which is somewhat important. In the end of the day, it could be that all your minimizers, if they exist, are just finite rank operators. So basically, then it's just a set of functions you can, so to say, look at. And then, in principle, you could use more standard methods of variational calculus to study this problem. But nevertheless, there is at least a strong indication that the minimizer, if it exists, is infinite rank. So here's the little proposition just before you deal with the variational problem. So assume gamma minimizes E gamma, and it has non-vanishing pairing. Otherwise, you're in the pure Hartree-Fock case, and then it's easy to see that the optimizer is finite rank, and you just have, basically you don't have really an operator, you just have a number of orbitals to deal with. But then you can also conclude, if the pairing does not vanish, the rank of this minimizer is in fact plus infinity. So you have infinitely many elements in the range of gamma. So this connects, in a sense, to a core problem in this variational calculus. Namely, at some point you want to understand the fall-off behavior of these minimizers, the spatial fall-off behavior of these minimizers. By this I mean the density associated to this gamma, or you can also say how this gamma XX decays as you go to plus infinity. And if you have an infinite rank operator, so then the density associated to this using the eigenfunction expansion. But now you have infinitely many weights, and it's completely unclear. Of course, these minimizers satisfy a certain Euler-Lagrange equation, which has a quite complicated structure, and we couldn't find any kind of method which was at least vaguely applicable to a certain kind of decay estimate for these functions. So the problem is, has this a certain decay, which is, so to say, connected to the infinite rank property? So you would presumably think there is an exponential decay. Nevertheless, it's completely out of scope to prove something directly in this case. You can, for each orbital, easily show an exponential decay, but then you have to get very precise estimates on these occultations. Some kind of hopeless task. So let me mention that the main results about this problem is now as follows. There is indeed a minimizer. This inf is attained whenever it's finite. And then the second theorem will give us a weak decay result about these minimizers. So take any minimizers, we can prove a decay. And the rationale will be that due to the properties of these minimizers, we can prove their existence, which sounds like a scholastic argument from the Middle Ages, that you use the property of something to prove its existence. Hopefully, I will have some time to explain to you how we use the properties of these minimizers also to prove the existence of minimizers. There is no circular conclusion in this contained. But nevertheless, this is a sort of funny twist of this kind of argument. So there are two theorems I would like to discuss in my remaining times, namely the existence of minimizers for this problem and also a certain decay estimate for the density of these minimizers. So there are two theorems. So theorem number one would be this is joined with Mathieu Devine from 2010. Is it published? So it says I for lambda has to satisfy a certain condition, that's clear. But in the full range, where this problem is bounded from below, I lambda is attained. There in particular exists minimizers. Moreover, you can show that any minimizing sequence, because you use some kind of concentration compactness arguments, are in a sense relatively compact up to translations. So it's an even stronger result, which is maybe also of interest for the time-dependent theory, which I don't discuss here. And this, in effect, once again, using concentration compactness arguments, boils down to the fact that you can prove a certain strict subadditivity condition. That the inf satisfies this property that for all lambda prime between 0 and lambda, you have this strict inequality. This is a standard argument, so to say, that if you have something like this, you might be able to show something like this. First of all, in this problem, it's easy to see that you have a non-strict inequality, but the point is to prove the strict inequality. However, now the point with this whole Hartree-Fock-Bogoliubov type theory is that it's absolutely unclear how to prove this subadditivity condition. There is no scaling argument that you can use, for instance, as you can do in many simple variation problems. You cannot just by a simple scaling argument show that such a thing is true. Also, because lambda is not quantized, meaning that it's not an integer number, you are not able also to prove this kind maybe by kind of an induction, as you can do in some kind of Hartree-Fock theories. So lambda is a continuous parameter, also an induction argument won't work. So you have to really prove this inequality by some kind of insight into this problem, and I claim the insight into this problem works with any kind of Hartree-Fock-Bogoliubov theory with attractive interactions. However, of course, the carrying out of this program might be quite different because you don't have the Coulomb potential. What I do here, I can do with lots of perturbations of the Coulomb potential, but if I have just a short-range potential, then it might be somewhat different. But the whole strategy in principle should work for a whole class of problems. And how to prove this subadditivity condition, which in particular yields the theorem, is that we have a theorem number 2, which says something about the properties of the minimizers. So I will have 7 minutes basically. Is this right? Okay. Okay, let me mention theorem number 2. So if gamma little gamma alpha minimizes the energy, then you get a quite weak decay information, which is is sufficiently strong to conclude the theorem number 1, as I will explain hopefully in my remaining time. That for all x, modulus x larger than say some r, the remaining integral decays like this. So C is constant, which may depend on the minimizer, but of course not on R, this form. So in a sense, these are somewhat weakly localized minimizers. So the whole crux here, so the proof of theorem number 1 will work using theorem number 2. Okay? How does it go? First of all, let me just mention how you would recover something like the proof of theorem number 2. So for the experts here, that if you have this minimizer, it satisfies, of course, a certain Euler-Lagrange equation, which in this setting looks like this. So there's a certain Bogoliubov mean field Hamiltonian, which depends on the minimizer itself, and then there's a certain Lagrange multiplier, the chemical potential, and then there is a certain finite rank part, which is not important in our discussion here. However, it turns out that, as I said, every method we could think of from the literature proving such a decay estimate for such a problem apparently doesn't work. And the proof consists in two facts. You have to get a very precise bound on the chemical potential. Morally, you would think if mu is strictly negative, you would be fine, but in fact you have to compare it to some kind of infimum of a spectrum of a certain associated two-body Schrödinger problem. And this is lowers even below 0, and you have to get a better decay, better bound on this mu. And then you can use this information to get some kind of localized operator inequalities that you can bootstrap in a sense to eventually to get to such a decay estimate. But let me just in the last 5 minutes explain why such a decay estimate can be used in the existence proof. And the argument is roughly as follows. First of all, we use as a general concept concentration compactness arguments adapted to this case. That is, we consider minimizing sequences. We know E is bounded from below, and in fact this is a coercive function, so the minimizing sequences are also bounded. And then we have to face 3 scenarios up to subsequences. A compactness, so in the sense that we have what we want, we get strong convergence, we are done. This is one scenario, we don't have to deal with it. This is what we want. The second scenario would be some kind of vanishing. But this is already hard to rule out for this problem because of the fact you get a vanishing for the density of gamma, little gamma, but this does not give you enough control to see what the alpha term does. So finally you have to discuss a two-body Schrödinger operator, which is similar to your PCS theory where you only have a kinetic energy part and a pairing part. And then you have to compare to these kind of zero energy level set to rule out the vanishing. So what I want to say, the vanishing again, in many cases is very simple to rule out. However, in this case already you have some kind of work to do. And then there is another scenario, and if you then rule this out, you're completely done. This is the dichotomy, that the sequence might split into some non-trivial parts, and this you want to rule out, and then you use this theorem number 2. How does that go? It goes like this. So the only thing I would like to sketch here is how to rule out the dichotomy. Well, this consists in seeing that if you have such a dichotomy situation that your minimizing sequence, which has total mass little lambda, splits into one piece having lambda 1 mass, so lambda 2 mass, 2 masses which are really non-zero, but of course they're bounded from above by your total mass of the minimizing sequence. And then you have a splitting of the energy in a way that you can then show that the infimum has to satisfy this equation. So the strict inequality fails. But in the end of the day, you want to show that this leads to a contradiction, hence this inequality holds. So this is the first information you get when you discuss the dichotomy. But the more important fact are that these infima are now attained. Also, there exists minimizers. little gamma 1, alpha 1, and gamma 2, alpha 2. For E number 1, respectively E number 2. Now you use these minimizers, and you now can apply theorem number 2, because there are minimizers, and you have certain decay estimates for these minimizers, and then you try to construct a trial state which even lowers the energy, and this gives you the desired contradiction. So what I want to say that is that using this localization property, you can now do the following. You take these two minimizers and you cook up, so to say, a new trial state. So you take this minimizer gamma 1, which is known to exist, and also the minimizer gamma 2, you localize them by some kind of smooth cutoff in space, which you can also do in this operator setting. And you separate them far away enough. You make, of course, errors. You localize the kinetic energy. You make an error which is of order 1 over r squared. You make further errors which is also of order 1 over r squared because of your decay estimate. However, you also see that there is a certain remaining attractive interaction of these localized optimizers. So you get an error which is, so to say, of the form, well, you say, fine, this is something I always get, there's something of 1 over r squared, this is something you cannot avoid by localizing the kinetic energy, for instance. However, you still get an effective long-range interaction, which is of this form, like 1 over r, which is also physically somewhat reasonable, because far away they look like 2 points with masses lambda 1 and lambda 2, which attract each other with this kind of law. So you get effectively another term which brings down the energy in total. So by choosing r sufficiently large, you can finally conclude that you can cook up a trial state, and this is my last remark here.
So you know this comes from the alpha or from the gamma?
This is from the gamma. The alpha doesn't play a role. I mean, the alpha has also a decay estimate automatically once you have a decay estimate for gamma. And then by choosing r sufficiently large, you get then a strict inequality of this form. It can do that the infimum is strictly less than this thing. But once you have this, and it's not easy, not hard to see that you get a contradiction to this equation, because then you can rederive a strict inequality which contradicts this. So this is the final rationale to establish in this little time subadditivity. I'd like to stop here and thank you for your attention.
Is the minimizer normal? So does it have alpha equal to 0 or not?
Okay, this is a good question. We don't know. So, first of all, it seems very likely that the minimizer, or there are minimizers which have alpha not equal to 0, just looking at the functional, because if you increase the alpha, you might superficially lower the energy. But this is a difficult question. So there's no rigorous proof for this claim, but Mathieu and his PhD student have done very intensive numerical studies, which for this model actually indicate that alpha is not 0, that pairing takes place.
I mean, in the usual BCS model, there is a spin which you don't have, and the spin plays a role. So
okay, this I was sweeping under the rug. The spin, when it comes to pairing, this is of importance, that we form the Cooper pairs in spin up, spin down. That we use spin 1/2 actually.
So you do have spin.
Yes, what I did here was without spin, but when it really comes to the pairing question, you should include the spin. Or you have to include the spin to get a, yeah. But there's no rigorous argument showing that alpha is not equal to 0. The only rigorous statement which I showed you is if you assume alpha is not equal to 0, you are also already in the infinite rank case. This is based on work on the Müller functional by Frank, Lieb, Saringer, and Siedentop. But that alpha is in fact not equal to 0. We don't know. The problem, sorry to say this, to show that alpha is not equal to 0 is that you cannot use a semi-classical. If you might think in some semi-classical approximation, you might see that alpha is maybe not 0.
Also,
You already lose. I mean, alpha is of the contribution from the pairing is of lower order when it comes to this limit, so it's hard to detect something, I guess.
also, if you are in a translation invariant case and you have some short range potential, then you can see that this is the case. But for that, you need something like stability of matter, so which you don't have here. But in general, this is a difficult question.
Other questions?
Did you consider adding the entropy term, relative temperature?
No, we haven't considered this. This is an interesting problem. But typically, these stars are considered to be 0 temperature, but it would be nevertheless an interesting variation.
No? Please. Thank you very much again.